Hi, my name is Alex, and I'll present our paper Characterizing, Exploiting, and Detecting DMA Code Injection Attacks in the Presence of an IOMMU. First, let's start with DMA. DMA, or Direct Memory Access, is a common hardware feature that allows an attached device to access the main memory without involving the CPU. That's devices like GPUs, SSDs, network cards, USB dongles, and many others. DMA also allows a malicious device to read or modify memory that it was not supposed to. This is called a DMA attack. It's a side channel attack where a malicious DMA capable device compromises the system. One notorious example is this thin FireWire unit, which is basically a Lenovo ThinkPad with a FireWire adapter and can be used to take over a target machine. You just approach the target machine, plug in the dongle, and gain control. Easy enough. To prevent arbitrary access to the memory, a modern systems have IOMMU hardware. The IOMMU works for devices just like the MMU works for processes. It provides virtual memory support for the attached device, meaning that the device can access only pages that are listed in the IO page table, and the page table is controlled by the operating system. So within an IOMMU, the device can access the main memory only via IO virtual addresses, IOVAs. And this prevents the device from accessing any memory pages that were not explicitly set up by the operating system. And this way, the IOMMU is supposed to prevent DMA attacks. First, let's see an example of how IOMMU is used in the DMA API in Linux, and then I'll explain briefly why IOMMU is insufficient to provide security. This is an example of a send packet. First, the device driver maps the buffer. That's the virtual address of the buffer in red. It allocates an IOVA. It updates the DMA map operation, updates the page table. That's the blue box on the side. And now we have a mapping. Now the red virtual address and the yellow IO virtual address point to the same physical page. Next, what happens? The device reads the buffer using the IOVA, which populates the IOTLB. The IOTLB is has the same function as a TLB for MMU. It provides fast lookups for translations. Now, when the operation is complete, the device driver unmaps the IOVA. It removes the entry from the page table, and it flushes the IOTLB. So without flushing the IOTLB, the device can still gain access to the physical page because of the fast lookup. We flush the IOTLB and thus prevent the device from accessing this physical page, and we free the IOVA. Now, a problem is the problem, and the problem is something that's called a subpage vulnerability. In the case of IO, many packets are much smaller than a whole page. It can be like an ARP packet, an ICMP, DHCP, any control packet. And in this case, a small chunk of the page is actually used. But when mapping it, the whole 4K is exposed to the device. And unsurprisingly, there were a couple of projects recently. One of them is the Thundercloud project, and it was showcased in NDSS in 2019. They chose an FPGA that can masquerade as an Intel NIC, and among other things, and gain access and act as a malicious device and compromise the system. Another was a work by Kupfer in his master's thesis, where he was able to take advantage of a DMA vulnerability bug in the FireWire device driver and actually execute a code injection attacks on the target machine. So the problem with these two jobs, what is missing is that there's no structured way. We don't know how to find new DMA vulnerabilities. We don't know how to assess a DMA vulnerability. Is it something that is very dangerous or not? And the most troubling one is we know that there are vulnerabilities, but how many are there currently in the operating system that we use? How leaky is the ship? And I'm here to try and answer some of these questions. So first, we'll talk about characterizing the subpage vulnerabilities and the code injection and attack attributes. And then we will talk about the rest of the contribution. So subpage vulnerability has 4 types as we see it. One is when a device driver, for some reason, maps its own metadata because it collocates the IO buffer and its metadata on the same page. But more often what happens is it's by OS design. And examples are FreeBSD and Windows, where they and macOS, where the IO metadata sits just in front of the IO itself. So there is no way actually to map the IO without also mapping the metadata. The third type is when you have 2 IOVs mapping the same physical page. One problem with this kind of vulnerability is when you unmap one IOV, the device can still access the same physical page because it can use the second IOV, which renders the unmap operation essentially useless from a security standpoint. And lastly, we have the incidental exposure. This happens usually randomly. The first 3 are easily detectable, detectable with static analysis. The last one has a random nature. What happens is an IO buffer is allocated and another buffer of a similar size is allocated from the same page. So when the IO buffer is mapped, all of the other buffers that reside on this physical page are also exposed. And we see how it can become a problem in the next slides. So let's see an example of something live. One example is NVMe fiber channel driver. And in the init request, when the host wants to read something or write something for a storage device via the fiber channel, the communication happens via DMA. And in this case, what happens is this command data structure, it's 96 bytes long, is mapped to the device. The second thing that happens is the response is also mapped, and its size is 32 bytes, sorry. And it allows the device to write to that page. So innocuous enough, but when we look into the data structure, we see that the command and the response both reside one next to the other, and essentially allowing the device both read and write access to the same page at the same time. And it also exposes all the other fields in this FCP operation data structure. One of those being FCP request, which contains none other than this callback pointer, which when overwritten will allow the device to effectively gain control of the machine, for example. Which leads us to the attributes needed for successful code injection attack. So you need 3 things. You need the virtual address of the malicious buffer. So how do you override this callback? And with the both read and write access to this page, we can learn the page address, the CPU address of this page, because it's one of the fields. One of the fields points to the head of the data structure set. The other thing we define is the callback function to override. And the third thing, we need an opportunity, namely that once the callback function was overwritten, it will not be reset and instead be executed by the CPU. And that's exactly what will happen in the case of the NVMe fiber channel operation. Next, now we see how dangerous subpage vulnerabilities are. Let's talk about detecting them. So we provide static analysis for the first three types, dynamic analysis for runtime analysis of your system, and we provide a kernel 5.0 analysis showing what kind of numbers or how many vulnerabilities are there today in kernel 5.0. We call our static analysis SPADE, and it works recursively. It starts from a DMA map operation, and that's an example. We see that pointer is mapped, and we look up and we see that it's a void pointer, which is kind of useless. But let's see where's FC DMA map signal function is called, and we see that we find it one example in NVMe init request. We find that the pointer actually is an op pointer, and if we scroll up the screen, we find the name of the data structure, and we analyze this data structure with tools like PA-hole. We find callbacks inside of it, and thus we find the vulnerabilities that we were looking for. Second, we have DKSAN. It's a runtime analysis used on a kernel address sanitizer, and you can read more about it in our work. And she provides these four types of vulnerabilities where a buffer is mapped randomly, in essence, and you find multiple examples of non-IO buffers being exposed. Both tools are open source. You can find them on GitHub. And finally, we provide a new compound attack. So the example is Linux kernel, where an IO buffer has SKB shared info, and it happens for specifically for all network buffers, and it contains a callback function. The problem is that it's not enough. We have no opportunity because the structure is overwritten after DMA map, and the problem is we don't have the CPU address. And because we have no more time, I can't go into details of a DMA attack, of a compound DMA attacks. So I urge you to read our paper. Thank you.
Thanks for the great talk, Alex. Let's see if we have questions posted on the Slack channel. We don't have any so far, so maybe I can ask you a couple of questions. So you talked about different subpage vulnerabilities, and then you mentioned that the OS metadata co-located with the IO buffers is a problem in BSD, Windows, and even Mac. Is Linux immune to this problem, this vulnerability? And if so, did the developers anticipate this particular subpage vulnerability in that they did not place the kernel data structures in the same page, and they were careful about that, or is it just by chance?
Well, the example I've shown shows that they didn't in NVMe devices. So the specific problem I was mentioning is for networking. So networking metadata is in all the systems is linear in the sense that the metadata and data are always on the same page. In Linux, it's just a matter of flexibility. You have the data, and then the metadata is on a separate page. But again, the final example that I just started showing in the talk of the compound attack is when we need to have more intelligence in our attack, namely locating the time of attack, when you can modify the call pointers, when to find them, obviously, and we find them in the metadata that is called SKB shared info at the end of the data page. So what happens in Linux? So you have the SKB, which is the metadata for a network IO packet. Then you have the data itself, and at the end of each IO packet, small and big, you'll have SKB shared info, which holds additional metadata and a callback pointer as well. So the short answer is no. There is no operating system today that does not expose a sensitive metadata in its IO path.
Mm-hmm.
So,
okay. So let's see. So the other question that I had was, you talked mostly about the code injection vulnerabilities. Are there also other problems like silent data corruption or something like that the devices can cause to the system, which may cause the system crash or something like that?
yes. So with it's just trivial attacks that well, data corruption is something that you can't avoid with software, because the data is written by the device. You don't know how it's supposed to look, right? So data corruption is something that we can't prevent. We can prevent access to things like the control path. You don't want to allow an attacker to execute malicious code with root credentials. Kernel panics, obviously, if you corrupt those callback pointers, just if you put a null in there, you'll get a kernel panic, and you don't need any compounder that for the callback pointer is there, and null is null. So yeah, there are different attacks. Just code injection is the most severe in my mind. So where you just can run any random code on the machine and just gain control. In theory, you can also silently try and steal data, like in the case of the metadata screenshot info. You have addresses for other pages for when the packet is made of different pages, different buffers. So in theory, you can probably change the response pointers before they are mapped, and thus make the OS map its own memory and send it to the attacker, for example. But it's a theoretical example where we don't actually change the code execution, but we can make something pretty malicious and scary to happen.
All right. Thank you. Very cool work.
Thank you.
Let me see if they have any other questions. So please feel free to post your questions about this paper on the Slack channel. I think Alex can answer them offline.